So again, what I'd like for you to do here is treat this first section as me putting down markers, if you like, for things we can come back to later when we need to apply these tools. What I want you to do, though, as I walk through these slides, is I don't want you to allow me to turn the page unless you understand what is on the page, okay? So don't allow me to move from one slide to the next, because then you go down that slippery slope. As soon as because you know what happens when I turn the slide and you're like, oh, I don't really understand what was on the last line of that previous slide. It sits in your mind, and then you sort of, it snowballs, all right? So let's try to do that. Let's try. But what I urge you not to do is don't try to retain everything, because there's a lot of information you're going to see today. Console yourself in that, as when we turn the page, say, yep, I understood what was on that page, which means that if you need to go back to it later on today or tomorrow to look at how did that go again, how did you do that, then you say, oh, I know I'll be able to figure it out because when we went through it, I understood it. Okay? All right. So I need a result which is going to be in much of what we do when we talk about pricing very simple fixed income instruments. And it's a result which comes from something that we refer to as geometric series. So what I have in mind here, just get my cursor off the slide. What I have in mind here is a sum of, from 0 to n, of a number z raised to the exponent I. And the fact that it's a number z raised to an exponent is what makes the series geometric as opposed to arithmetic. All right, so that's what the geometric piece of this is, just because we're raising this term z to a power called I. So what I want to do is I want to come up with an expression for this sum, all right, which is convenient to work with. So first things first, look at the first line. So there's a couple things going on there, right? So this is just notation. The best way to read this equation the first time you see it is to read it from the right to the left. If I put the thing on the right and I said, okay, I've got a bunch of numbers. I've got 1, then I've got plus z squared plus on, and then all the way to z to the power n. Now, where n is some number greater than 0. So, for example, suppose I said to you, I've got the sum from I equals 0 to 3, z to the power I. Right? Then this would just be z to the power 0 plus z to the power 1 plus z to the power 2 plus z cubed. So that's an example of what is stated. Let me just, I flicked my slides unintentionally here. That is what is as an example of what is stated in that first line. All right? So you may say, well, I'm confused because in your first line, the first term on the right-hand side is 1. And that's because any real number raised to the power 0 is 1. This is true so long as z is not equal to 0. Okay? All right. So, so we could write this term here as 1. Okay. So what am I doing in the middle of the slide? I'm just employing a trick, which, you know, some people are really good at seeing that there are neat tricks you can apply to get expressions which are convenient to work with. So what I'm doing is I'm saying, let's multiply both sides of the equation, right, by 1 minus z, which is really all I'm saying is take the sum on the right-hand side and subtract from the sum z times the sum. Do you follow? Yeah. So I'm saying, if I were to say to you, if I were to take the right-hand side and say, multiply it by 1, you'd look at me like I was weird, because you'd say, well, if you multiply any number by 1, it just returns the number, right? So you say, well, what are you doing here? So I'm going to be multiplying the sum by 1, but I'm also going to be multiplying it by minus z. I can unpack that, right? If you look at what I've done here, apologies if I'm going off camera for the folks online, if you look at what I'm doing here, right? 1 minus z, right? And what I'm doing in the next line is I'm taking 1 and I'm multiplying it by that, which just returns that sum. And then I'm multiplying by minus z, which minus z times 1 is minus z. Minus z times plus z is minus z squared. Minus z times plus z squared is minus z cubed, which is not here. And it goes all the way to minus z n plus 1. Can you see why it's n plus 1? Because the last term is minus z times z to the power n. Right? And that is equal to minus z n plus 1. Does that ring a bell? It comes from that rule. For example, if I'd said to you, what is z squared times z to the power 5? What would you say? Can you write that in a more convenient expression? And you'd say, sure, I can write this as z to the power 7. You can add the exponents. So that's where I'm getting this n plus 1 from here. Because the number z is just z to the power 1. Does that make sense? Okay. So if you now look at, you notice I've written the second line in the middle equation. I've written it in this kind of staggered way. And I've written it in a staggered way so that to make it obvious to you that, look, for every positive number with a z, I'm going to have a negative number. Except for the first term, which is 1, and the very last term, which is going to be minus z n plus 1. There's going to be no offsetting term in the first piece of the sum. So that means that when I multiply the sum by 1 minus z, all I wind up with is 1 minus z to the power n plus 1. But I want to get back to the sum of z to the power I. That's what I started with. But you say, that's easy. All you've got to do is you've got to divide by 1 minus z on both sides, and you get back to the sum. You follow? Now you're thinking to yourself, what on earth does this have to do with bond pricing? Right? Well, what this has got to do with bond pricing is that these terms that I'm here referring to as z, z squared, z cubed, right? They are going to represent the present value of cash flows of bonds. So this is a very, very fundamental and important concept to master. All right? And all you need to do is see this trick once and you say, okay, now again, in 5 minutes' time, you're going to forget what the expression for the sum of z to the power I is. And that's okay, because you can always go back and look it up. Okay? But I need for you, before I flip the page, I need for you to say, all right, guys, let's move on. I'm okay with this. All right? So, again, the important thing to remember is, what have I got here? I've got 1 minus z times the sum from I equals 0 to n, z to the power I is equal to 1 minus z to the n plus 1. Right? That's what I've got when I get to the end of the second equal sign. Or the third equal sign, I should say, sorry. All right? And then I'm saying, but I want an expression just for the sum. Well, that's easy. This should have a bracket around it. That's easy. In order to get this by itself, you just have to divide by 1 minus z. So do the same thing on both sides, and you get what you want. Does that make sense? All right. So now you'll notice that there is a 4z not equal to 1. And that's very important to bear in mind, right? You can't divide by 1 minus z when z is exactly equal to 1, because then you'd be dividing by 0. And for philosophical and deeply mathematical reasons, I'm not going to go into that, but I'm going to ask you to take my word for it, because it turns out it's true that dividing any real number by 0 is meaningless. It's undefined. Okay? So just remember that you can only do this trick. You can do everything up to here, but if z is 0, you can't. Z is 1, sorry, you can't do this last piece. And of course, it turns out that for our purposes, z will almost, no, not almost, z will never be 1. So we are going to employ this trick all the time. And we're going to employ a variation on this trick, which is on the next slide, and this involves something called a limit. Okay? Now, I don't want to get technical about what we mean by limits, but I want you to have some kind of intuitive feeling for what I mean by a limit. So couple things here. So I'm going to say, for the absolute value of z smaller than 1. All right? So that's what this, putting z in between these gates, that's what that means. That refers to the absolute value of z, right? So the absolute value, say for example, just to remind you, say for example z was minus 0.5. Then the absolute value of z is just 0.5. Does that make sense? So now what I'm going to do is I'm going to say, I want to take the limit of this expression as n, and remember where n is over here, right? N is determining how many of these terms we add together. I now want to say, can I contemplate what would happen if the number of terms I was stringing together, right, if I allowed that to go to infinity, right? Now, your first guess would say, well, hold on a second here. You're adding numbers together, right? Like, for example, the first number is 0.5, the second number is 0.5 squared, and so on and so forth, right? Or the first number may be 1, and then 0.5, then 0.5 squared, and so on. You may say, if you add an infinite number of numbers together, then you must, the sum of those numbers must explode. It must become infinite itself. And the answer is not so fast. So this is where you're bumping into a property. If you want to be fancy, you're bumping into a property of a particular kind of geometric series, which is said to be convergent. And convergence means that precisely when you allow the number of terms in this particular sum to increase without limit, to go to infinity, then the sum itself does not explode. It is bounded. There is an upper limit which it cannot exceed. And this is going to be very important when you understand continuous compounding, which is a variation of calculating the yield to maturity, if you like, on a bond. It's to do it with continuous compounding. Okay? So let me just go to the previous slide to show you how you should think about the limit, all right, what I've done there, because this doesn't tell you much. It just says, oh, the limit as n goes to infinity is 1 over 1 minus z, which is a very pretty result because it's such a simple expression, right? But how do I know that's true? So let me give you some insight by backing up and going to my previous slide, all right? So now, not only is z not equal to 1, but I'm going to assume that the absolute value of z is smaller than 1, okay? So what I'm doing is I'm saying, what have I got? I've got 1 minus z to the n plus 1 minus z. So this is what I want you to do. All right? So I'm really taking the limit as n goes to infinity of that expression there, 1 minus z to the n plus 1 over 1 minus z. Now remember, the important assumption I'm making here is that the absolute value of z is less than 1. All right? An example of the absolute value of z being less than 1 is to set z equal to 0.5, like we did over there. That conforms. This, and I'm just using this for the sake of illustration, but this assumption is consistent with this condition. Because this limit that we're going to find only exists if this is true. All right? So think about this expression. And think about making n increase. So you'll notice that n is only present in that term of the expression. So the only thing we really need to figure out is what is happening to z to the n plus 1, right, as we allow n to go to infinity. Because it's the only term in the expression that is affected by n. And now here is the key. Z is smaller than 1 in absolute value. So take 0.5. So if you set n equal to 0, then you've got 0.5 to the power 1. That equals 0.5. Okay? If you set n equal to 1, then you've got 0.5 to the power, can anyone tell me? 2. What's that equal to? If you set n equal to 2, you've got 0.5 to the power 3. What's that equal to? 0.125. You see it's getting smaller? So remember, this is just this term, which is just one term in this expression. So what do you think is going to happen to z to the n plus 1 as we allow n to become huge? It's going to approach 0. And if that goes to 0, then it means that in this term expression over here, if this thing goes to 0, you are going to have Does that make sense? That's a beautiful result. And it's the result which allows you to think about expressing the price of a bond, which makes coupon payments. Does everyone know what a coupon payment is when I talk about a bond? So bonds are contractual arrangements entered into between buyers and sellers, borrowers and lenders, and the borrowers receive a bunch of money up front by selling a bond, and they make promises to pay money back. And in some very simple bonds, like treasury bills, they only make one payment. And the date at which they make the payment is called the maturity date of the bond, because after that payment is made, all obligations are extinguished. Other bonds are more complicated. They make a sequence of payments. These bonds are called coupon bonds. Well, this will become more obvious later on. Now, imagine I tell you that I've got a coupon bond, right, which pays coupons forever. You'd be inclined to say to me, oh, well, that bond is going to have a price which is going to be infinite. Because you're going to say, if you add up all the coupon payments that that bond makes, right, and the coupon payments go on forever, let's say it makes annual coupon payments, right, then the bond price must explode. And we will learn that because of this result, right, the price of that bond, which makes payments forever, does not explode. And there is, in fact, a finite price for the bond. Okay? The government of the United Kingdom has issued these bonds in the past, and in fact, at one point in time not too long ago, was considering issuing them again. And in the United Kingdom, these perpetuities, that's what the technical term is, these perpetuities are called consols. That's the name of the bond, all right, which is not particularly important, but it relies on this result. So that's the big result from geometric series that is useful in fixed income mathematics. Okay? All right. So there it is again. There's the limit. And now I'm just going to have some fun. Because now I'm going to say, well, are there other things I can wring out of this result? And yes, there are. You can fiddle with the sum. You can get cute, and you can say, oh, what if I sum from I equals 0 to n minus 1? Well, if you go back, remember when I was summing from I equals 0 to n, I got 1 minus z to the n plus 1. That n plus 1 came from the z being multiplied by z to the n. Well, if I'm now going to stop at n minus 1, when I multiply by the z, I'm just going to get z to the n. So that's what I'm showing over here. You follow? All right? And then I'm saying, so I equals 1 to n, sum. So you notice the difference. This I equals 1 to n is not I equals 0 to n. See? Previous slide, I equals 0 to n was that expression. So someone is going to stand up and say, what happens if the first term in the sum is not the number 1? What happens if the first term in the sum is the number z? Well, if the first term in the sum is the number z, then you're not starting I at 0, you're starting I at 1. But if you know how to start I at 0 and go to n minus 1, you get that, and you say, but that is just equal to z times that, because I know what this is. This, on the left here, is that. By multiplying by z, right? So let me back off here. Let me try this. So what we're doing there, if we just unpack that, is we're saying this is z, sorry, 1 plus z squared to z n minus 1. Agreed? And I know I can write that as 1 minus z to the n over 1 minus z because of what I learned on the previous slide when I was summing from 0 to n. All right? So now I can say, okay, what does I equals 1 to n look like? Z to the I. Different from this because it starts at 1 and it ends at n. This one starts at 0 and ends at n minus 1. Right? This one, we know from this, is 1 minus z to the n divided by 1 minus z. So what's this one? Okay, so the first term in this one is z plus z squared, and it goes to z to the n. All right? But you would tell me that it's exactly equal to this sum if you just multiply it by z. Do you agree with this? But in this bracket is just this. So this is just that. And the rest follows. So it's just cleverness, right? It's just being cute with the way you arrange these expressions. And you try different tricks to come up with just convenient ways, nice compact ways of writing these things. I mean, who would have thought that an infinite sum of numbers raised to exponents would collapse to an expression 1 over 1 minus z, provided that z was not 0 and in absolute value smaller than 1. I mean, that's just not obvious. But so cool when you see it, but more important than being cool, it's so useful. Make sense? So now, there are lots of tricks like this. This is just scratching the surface, right? You can do cool things with all kinds of expressions, geometric series. But we don't need to spend all of our time today talking about geometric series because we've got much more important things to do. But these results are going to crop up from time and time again. And when they crop up, I want you to be, I remember that from Monday morning. Yeah, I know I can go back to those 3 slides and I can look it up again if I want to remind myself how the tricks work. Okay? So if I've got this expression, right, from I equals 1 to n, so all I did is I dropped the 0, right? So I've got an expression for I equals 0 to n, and I know what its limit is. Now I've got I equals 1 to n, and I want to take the limit of that. And now the limit of that is z over 1 minus z. So when the series started with a 1, the limit was 1 over 1 minus z. When the first term in the series was a z, the limit is z over 1 minus z. All right? And then you can say, well, what if I start at something, imagine m is 3 and n is 100, so I'm summing from 3 to 103. Well, there's an expression for that too. It follows the same form. And you can again take a limit. So once you've seen one of these cases, with a little bit of cleverness, you say, wow, there's all kinds of things I can, any one of these sums I can write down an expression for, and I can also evaluate the limit, provided that the absolute value of this z term, which is in all of the terms in the sum, is smaller than 1 and not equal to 0. And that is going to turn out to be useful, very useful. Because if you think about it, when we price bonds, we take cash flows, right, over time. So let me just give you a quick insight here. I hope it's an insight. When I price a bond, I may have, think of a timeline, and suppose that I'm trying to work out the price of a bond today, and I'm just going to call today times 0, because it's convenient to do so. And my bond is going to make annual cash flow. So imagine I'm measuring time in years. And it may go on. But at each point in time, the bond pays, let's say, a coupon, which I'm going to call C dollars. C for coupon. It can be any number you like. Right? Well, the way you work out the value of the bond is you apply something which is called a discount factor to the cash flows. And you may have heard of this term, the discounting, when you apply the discount factor, it's called discounting the cash flow. And that is supposed to take care of something called the time value of money, which you may have heard of. That's actually not the best way to think of it, it turns out. But let's go with that for now because it's what you're familiar with. Later on, I'm going to disabuse you of that time value of money stuff. So, but think of the z's that we're talking about here, which have got no bearing, apparent bearing to finance, or relation to finance. The z's are going to be the terms which we multiply these payments by in order to do this discounting, which is bond pricing. That's where we're going. So that's why I have to start with something which seems completely unrelated to finance, which is, how do you figure out the sum of z to the power I? All right, so just to keep you on track and not to have you panic that we're going to just do mathematics or arithmetic, at least for the sake of the arithmetic. That's never the intent.